Hello, everyone. Welcome back. So, I want this out of my way. I'll hide it. In this lesson, we are going to be going forward and talking about probability, which you might have some experience with, right? So, we will do some work with stuff that involves cards and dice and coins, right? That's where a lot of fun things with probability come up. You will also see sometimes where we're tying in things with combinations, right? Like how many possible ways are there to get a certain number of cards, or how many possible ways are there to choose heads or tails, right? So that stuff will come. Not a ton today, but you will see some with it. So our focus in this lesson is going to be to identify sample space. Maybe you've heard of it, maybe you haven't, we'll define it, and events, and calculate probabilities of both equally and unequally likely outcomes, right? So as I was just talking about coins, right? Equally likely, heads and tails, right? There's a 50-50 chance. Unequally likely, right? If you don't have, if they don't have the same probability of two events, if two things don't have the same probability of occurring, those are unequally likely outcomes. So we're going to talk about how you calculate probabilities in a variety of different situations. So let's see what we already know about probability. So find the probability of tossing a head on one toss of a fair coin, right? That's 1/2, right? Or you got a 50-50 chance. What about tossing two heads in a row on two tosses of a fair coin, right? So my possible outcomes are I can get two heads. That's what I want. I can get a heads and then a tails. I can get a tails and then a heads. Or I can just get two tails. So I have 4 possible outcomes. Only one of them is which is my desired outcome. So I have 1/4 for 0.25. Right? My chances, the probability of that happening is smaller. What about drawing a queen from a standard 52 card deck? So hopefully you know something about cards, right? How many queens are there in a standard deck of 52 cards? Well, I have 52. You can almost think about this as, well, I'm picking one, 52, choose one. Oh, that's just 52, right? And how many of them are queens? Well, I've got 4 queens, right? So what is that? 1/13. All right. So the probabilities, or these probabilities are examples of probabilities of events that are equally likely, right? Tossing a coin. When you're picking one card from a deck, there's only one of each card, right? So that's what, right? There's 4 queens, there's 4 kings, there's 4 jacks, there's 4 nines. All of those events are equally likely. So it's an event E is an event in a sample space S of equally likely outcomes, and the probability of the event E, is P of E, so there's the notation, the number of outcomes in E over the number of outcomes in S. The number of outcomes, so like how many times can that event happen over how many possible outcomes are there? That is a sample space. If I went back to this slide back here, oh boy, this right here is my sample space. Right? If I'm listing out my outcomes, like what are all the possible things that could happen when I do this, that is the sample space. Right? The event is the desired outcome. That was my desired outcome. Since each card is equally likely to be drawn, the probability of drawing a queen from the standard deck was 4/52, or 1/13. A red and green die have already been rolled. What is the probability that the sum, if I add them together, I get 9? Well, how many sums are there total of 2 die? Well, I'm going to get 36, right? If I take one die, I have 6, choose 1. The other one, 6, choose 1. So that's going to give me, well, that's just 6 times 6. I have 36 possible outcomes. That's my sample space. How many of those 36 are going to have a sum of 9? Well, let's think through it. If I have two die, I could get a 6 and a 3. I could get a 3 and a 6. Right? Think about them as like, this is dice 1, this is dice 2. What else could happen? I could get a 5 and a 4. Or I could get a 4 and a 5. Those are my only ones, right? I can't get a 2 and a 7. It's a standard die. So the probability, or the probability of the sum of 9 is the number of ways to sum to 9. Well, here's 4. Over the number of ways to roll 2 die, 36. So I've got 4 over 36, which is 1 over 9. These are all equally likely outcomes, right? Any sum, right? Like each one, like I'm not, this individually, I'm going to get the same probability of getting this individually, right? It's a fair die. Like me rolling a 1 on one of them, I've got a 1/6 chance. Me rolling a 6, I've got a 1 out of 6 chance. The sum is a little different, and we'll get into that in a moment, but each one of these individual events is equally likely. These are 2 different events because this is 2 different die. So what about the probability of an event of unequally likely outcomes? So the probability E is an event in S, and the probability of E is the sum of the probabilities of all of the outcomes in E, as defined by a probability distribution. So a probability distribution function, sometimes that's PDF, a function P that assigns a real number to each outcome in a sample space such that the probability, what does this mean, is between 0 and 1, right? It has to add, like when I take every possible outcome, it has to add to 1, everything in that sample space. Oh, sorry, that's what's down here. The sum of the probabilities is 1. But each individual probability has to be between 0 and 1, right? Like that 1 is 100%. 1. So if we look at these 2 probability distributions, that's what these are. Let's see what happens here. If I do 1/5 and 1/5, that's 2/5, 4/5, 6/5. Huh, that doesn't make sense. Nope, that doesn't work, right? There's something wrong with that. You're not going to have probabilities that are not adding to 1. So like if that occurs, it's not a probability distribution function. It's not valid. This one works, right? If I take 0.35, 0.35 plus 0.15 gives me 0.5, plus 0.4 gives me 0.9, and then 1, right? The sum is 1 for that. Okay. So let's do this. Let's construct a probability distribution for an event. Let me erase this. Okay, well, that's okay. Well, sorry about that. What is the probability of rolling a sum of 4 on a single roll of 2 die? So we already talked about how there was 36 possible outcomes, right? It's 2 fair die. But let's talk a little bit more about why that's the case, or what we can do with this, or how we can write it out. Like, how many ways are there to get a sum of 2? You can't get a sum of 1. That's not possible, right? So, well, my only way of doing this is if I get a 1 and then another 1. So there's going to be 1 out of 36. My only way to do 3 is if I roll a 1 and a 2, or a 2 and a 1. So there's going to be 2. Well, there's a nice way I could write this out. Let's see. I'll say this is one of mine. 1, 2, 3, 4, 5, 6. And the other one, 1, 2, 3, 4, 5, 6. Right? And you see like a nice line out of it. So I can get a 1 and a 1. I can get a 1 and a 2, a 1 and a 3, a 1 and a 4, a 1 and a 5, a 1 and a 6. You get a 2 and a 1. You get a 3 and a 1, 4 and a 1. I don't know if you guys want me to actually write this whole thing out. I'm not going to, right? But you can see kind of what's happening or what. There's some nice symmetry that happens with this too. Right? Some nice patterns that we can see. 2 and a 4, 2 and a 5. I'm going to stop after this one. Couldn't stop myself. So how many ways are there to get 4? Right? So we can kind of see, maybe I'll do some highlighting here. This is my only way of getting 1. I'm sorry, getting a sum of 2. Here, that's my sum of 3. Okay, let's keep going. Here, 3 and 1, 2 and 2, 1 and 3. That's a sum of 4. So this is going to be 3 out of 36. I don't know what I'm doing now. I didn't get a highlighter, sorry. Here, along this diagonal, I've got 5, 5, 5, 5. Okay, so I've got 4 out of 36. Well, let's see, on that next one, I don't have them all written out. I could add them in. You get a 5 and a 1, a 2 and a 6. These are all going to sum to 6, aren't they? 2 and a 4 is 6. 3 and 3 is 6. 2 and 4 is 6. 1 and 5 is 6. So I've got 1, 2, 3, 4, 5. What about 7? 1, 2. Man, I should have just finished writing. 4, 3. 3, 4. 5. Nope, 2, 5. 1, 6. I couldn't read my own handwriting. 1, 2, 3, 4, 5. Oh, I've got 6. But then what happens? That's my longest diagonal. Oh, and then I think I'm going to go back the other way. If you don't trust me on that, go for it and count. Look at that nice symmetry. We should probably validate that this is true, because what should they add to? Right? If this probability distribution should add to 1. Was I correct? Let's see, this is 6, 10, 15, 21, 26, 30, 33, 34, 35, 36. Yep. Right, so the sum of it is absolutely 1. Right, the sum of all of these possible probabilities or outcomes in my distribution is 1. Adds to 1, sums to 1. Oh, I didn't even answer the question, did we? So to answer this question, we can answer a ton of things now. What is the probability of rolling a sum of 4 on a single roll of 2 die? Well, there we go. 3 out of 36, right? Or if I want to simplify that, what is that? 1 over 12. But you could be asked tons of questions now, right? With this distribution, you can pull information out of it. Like, what is the probability of getting an odd number? Of rolling rolling a sum that is odd. Oh, well, I'm going to take that, and here I've got 3, I've got 5, I've got 7, I've got 9, I've got 11, and I could take those probabilities. This is the nice part of the fact that we didn't simplify. 4 over 36, right? I'm just going to sum their probabilities. Each one of these events is not equally likely. There's different probabilities, so I need to look at them individually. 6 out of 36. I asked a question and never finished it. 4 out of 36, 2 out of 36, right? And so you've got 6, 12, 16, 17, 18. 18 out of 36. Whoa, it's 1/2. Neat. Okay. Oh, of course, there's another. Sorry, guys. What is the probability of rolling a sum? Ooh, see, this is a fun question. I got ahead of myself. Divisible by 4. Well, okay, so which ones are divisible by 4? 4, 8, and 12. So those are not equally likely. Let's see, I've got 3 plus 5 plus 1 out of 36. So that would give me 9 out of 36. This was the original question. This was my made-up question. This was question 2. Pretty neat. So if the sample space has equally likely outcomes, the probability of an event is determined by counting, right? The number of outcomes in E and the number of total outcomes in S. The number of outcomes in the event happened and the number of outcomes where the event happens and the number of possible outcomes at all, the sample space. So the event over the sample space is going to give you the probability of the event occurring. If S, the sample space, does not have equally likely outcomes like what we just saw, determine the probability function, like what we just did, right? List out your possible outcomes, list out your sample space. Then the probability of an event is determined by adding the probabilities of all of the outcomes in E, right? All of the ones that contain that, let's add them together. So the multiplication principle of probability. Suppose an event A has probability p sub 1 and an event B has a probability p sub 2. Under the assumption that A occurs, then the probability that both A and B occur is the probability of the probability of A times the probability of B, right? P sub 1 times, you're multiplying together their probabilities. It's kind of like what we did with the dice, right? What's the probability of me getting a 3 and then getting a 4? You just listed out the sample space. Even though we were doing it with addition, we listed out all of those sample spaces, right? So 1, 2, 3, 4, 5, 6. I'm not going to do the whole thing again. Don't worry this time. The probability of getting a 3 and then a 4, well, that's only going to be here, right? That's the only place that there's a 3 and then a 4. Not a 4 and then a 3. It's not a 3 and a 4. It's me getting a 3 and then a 4. So that would mean that I have to, well, that's 1 out of 36. We know that. Well, where'd that go? From that sample space, from that picture that we drew, right? However, well, think about it in 2 separate events. My pen disappeared. No, it's there. What's the probability of getting a 3? Well, that would be 1/6. What's the probability of getting a 4? Well, that would also be 1/6. Well, the probability of getting a 3 and then a 4 is going to be 1 out of 36. Multiply that, right? So this is under the assumption that A occurs. So we also have this idea, and we're going to get a little bit more into this in the next lesson, okay, of independent versus dependent, right? So right now I'm going to kind of just explain this piece, and then we'll go more into independence in later. Some of you guys might have experience with it, but we're going to go into that a little bit later. So the probability of A and B, you might know a notation that looks like this. Intersect B is the probability of A times the probability of B, right? That's that multiplication principle that we just talked about up here. However, this is if the 2 events are independent, like one doesn't depend on the other. One happening doesn't lessen the chance of something else happening, right? However, if they're dependent, meaning one occurring causes the other one to change, right? Like if they happened in a different way, the other one would change, then that would be the probability of A happening and B happening is going to be the probability of A, right? You start the same way, times the probability of B given A. This multiplication principle assumes that A has occurred, right? But these don't depend on each other, so I don't need to take A into account when I'm looking at B. For this one, it says the probability that B happens given that A already happened. Okay? So independent versus dependent, and again, we're going to get into this a little bit more later, but is it possible for the event to happen in any order? If the answer is yes, does one event in any way affect the outcome or the odds of the other event? If the answer is yes, then it's dependent, like they depend on each other. One change is going to impact it. Whereas if your answer to this is no, is it possible for the events to happen in any order? No, then it's automatically dependent. You don't need to keep looking, right? You can't switch the order. They're not independent, they're dependent. Does one event affect it? No. If one doesn't affect the other, then they're independent. Okay. So if the event B depends on the event A, then the probability of B given A, so that's this, right? We're going to go down here, is the probability of A and B over the probability of A. Interesting, right? So that's what changes here. You can kind of see like what would happen if you went and replaced this. What would happen to these? Oh, like, so we need to take this into account because this is not, if the events are dependent on one another, this is not going to be the same thing as just the probability of B, right? It wouldn't be equal to the probability of B, which is why we need to take that into account. So the probability of B given A is the probability of A and B over the probability of A, right? It's like you're narrowing in your focus. So let's take a look. So multiplication principle property, we're going to apply it here. Mr. Getz always gets Ms. Getz a box of chocolates for Valentine's Day. That's so nice. Ms. Getz's favorites are chocolate creams, but all the chocolates look alike on the outside. If 4 of the 12 creams are vanilla, what is the probability that both her picks turn out to be vanilla? This is dependent. Why? Well, what happens? After she picks one, the chances of her next pick are not the same, right? Like once she picks one, what happens? It's dependent. Like her picking the first event, like her picking one is going to change how many options she has to pick from, right? And that therefore it's dependent. So the probability of getting a vanilla and then another vanilla is, well, first it's 4 out of 12, right? There's 4 total out of 12. But then once she picks the first one, if this is vanilla, check, she got it. There's only 3 vanilla left and 11 total left, right? That's dependent. So this right here is the probability of getting a vanilla. This is the probability of getting a vanilla given that she's already gotten a vanilla. Oh, wait. That was a poor. Nah, I don't know if I wanted to go that direction. I take that back. This is the probability of taking vanilla, like from the total, now that there's already 1 vanilla gone. And the total has been reduced. What is the probability that only the first one is vanilla, not the second one? Well, the probability that the first one is vanilla, that doesn't change. Sorry. And I'm going to write not vanilla. 4 out of 12 times, well, how many not vanillas are there? There must have been 8. There's still 8, but now there's only 11. So that gives me what? I didn't even finish this. 1 over 11? Is that right? Right, 12 over, yeah, that's just going to simplify to 1 over 11. 12 over 12 times 11. Right? Yeah. Second guess myself there for a second. This, well, I've got, what is this? 1/3, 8 over 33. The larger chance of that happening than of me getting 2 vanillas. What is the probability that the first one is not vanilla, the probability of not vanilla, and the second one is not vanilla? So let me see. Not vanilla, I got 8 out of 12. Not vanilla, well, I've already picked a not vanilla. So there's 7 out of 11, right? So what does that give me? 14 out of 33. Right? You can think about the sample space, like how many different options are there? That would be a lot to write out. And so that's where we're coming up with this. But you could think about that. What is the probability that they are both, wait. Oh, maybe that wasn't what I was supposed to say. Sorry, guys. Let's say, what's the probability that the first one the first one is not vanilla, and then the second one is vanilla. Okay, let's see. The first one's not vanilla would be 8 out of 12 times the second one is vanilla. Well, there's 4 vanillas left out of 11, right? So like after you've taken a one that's not vanilla, you have a higher chance of getting it because there's less in there. So that's going to give us 8 over 33 also. It was like, right? Yeah, pretty cool. So let's go in a slightly different direction. This still relates, but let's look at like pictures of this and Venn diagrams, which I'm sure many of you guys are familiar with, right? In a Venn diagram, so each circle represents an event and their overlap is the event is like the place where they both happen, right? So we are going to be shading these. So if I shade all of A and all of B, including their intersection, this is what is referred to as P of the probability of A or B happening. And so I could fill these with probabilities too. This would be my notation for it, the probability of A union B. Union. The probability of A and B happening is the probability of A intersect B. Well, what does that look like? So this is just the intersection. This has to be the probability that both of them occur. Well, that's just going to be the middle part, right? So you can think about it visually too. So the probability of A equals the probability of A not B plus the probability of A and B. So it's the probability of A intersect not B, right? That's what that notation is, B prime, like the complement of B, plus the intersection of A and B. No, it's this, right? That's just the probability of A. So I'm doing, if it was just, because you could represent this differently too, right? Like I could get rid of this middle part, and that would be the probability of just A happening without B being involved, like solely A. Right? So the probability of not A or B is the probability plus the probability of A or B is their intersection, right? The complement of their intersection, no, of their union plus their union is just 1. Oh, let's see what happens here. Let's see if we can picture this. Where's my highlighter? Here, the probability of not A or B. So not A would be everything outside of A. Or B happening. Okay. Oh, okay, I'm gonna shade it as we do it. Let's pretend none of that is shaded. So the probability of not A would be everything around here. This would be not A. Oh wait, it's not A or B. Scallon. Oh darn. It's not A or B. Not A or B would be this whole part outside. right? Like this is the probability that nothing occurs. Neither one of them happens. Neither one of those two events, A or B, whatever they might be. Ooh. Okay, if I add to that, this is going to look like the same color. I can't do that. The probability of A or B, well, we have that up here. That's this, right? So that's all of this fun stuff. We know that that's just one. That's what I've indicated here, right? So that's the same thing. I could rewrite this way. The probability of A union B complement, not A or B, right? So that's just everything. That's just telling me to shade everything, right? So interpreting that notation and what it visually looks like. This over here is William Venn. Oh, not John Venn. Wow, sorry. I feel like I need to, right? Oh, Venn diagrams. I'm not super familiar with this, but if you all know Alice in Wonderland, there's a lot of math involved. Miss Getz knows a lot of it. You are welcome to reach out to her to chat about it. And this is, oh no, I don't remember his name. The person who wrote it, Carroll. Lewis Carroll. Okay. So let's keep going with Venn diagrams here. So at a certain fast food restaurant chain with a redheaded girl as a figurehead, well, what could this be? The probability that someone orders a Frosty is 0.2. The probability that somebody orders French fries is 0.8. The probability that a customer orders both is 0.1. Find the probability that a customer orders all of these things. So let's fill in our Venn diagram. Let's label it. So I'm going to say that, let's see what my events are going to be. Somebody orders a Frosty. I'll call this one F. Somebody orders, oh no, I'll call it FR. I'll call this FF. Frosty and fries. So the probability that someone orders a Frosty is 0.2. The probability that somebody orders French fries is 0.8. So that's a whole circle. But I know that their intersection is 0.1. So I'm going to actually start from the inside and work my way out. Why didn't that dot work? My goodness. Kind of there. So this whole French fries, the probability they order French fries is 0.8. But I want this whole thing. Why is my dot not there? To be 0.8. So this part where it's just French fries is 0.7. This part where it's just, darn, I wrote it in the wrong place. It's very, this is just 0.7. This is just 0.1, right? I want this whole circle to be 0.2. I want this whole circle to be 0.8. Right? So let's just make sure. What does that add to? Let's see. Is there anything that goes on the outside? If I add up those probabilities, I get 0.8 plus 0.1, which is 0.9. Oh no. That means that there's a 10% chance there's 0.1 out here, right? Where somebody orders neither a Frosty nor fries. Not sure what they ordered, but they ordered neither. All right, so now that we have this, let's answer some of these questions. What's the probability that a customer orders fries but not a Frosty? Well, we've got this in our right over there already. 0.1, 10%. They order, oh my gosh, I'm reading it wrong. I wish there were different letters. Okay, fries, let's try that again, but not a Frosty. That's going to be 0.7. Frosty, but not a fries. 0.1. Neither a Frosty nor fries. Or fries. 0.1. Right? That's what we came up with over here. Fries. Oh, this is interesting. What is the probability that they get fries given that they ordered a Frosty? Okay, so how many of them, what is the probability that they got a Frosty? Right? So this is that notation where it's the probability of fries given Frosty. my letters are confusing me if you haven't recognized that. I poorly chose letters. Get the probability of French fries given Frosty. So are these right? Frosty? This is French fries. Yes. Okay. So if we go, I don't know if I want to go all the way back on my slides, but how you would write this is saying, well, this is going to be the probability that they got both, their intersection, over the probability that they got French fries. Right? That given becomes my like total because I'm narrowing in my focus. So the probability that they ordered both, we know that is 0.1. Over what's the probability that they got French fries? The probability, no, that they get a Frosty is 0.2, right? And so then I can go ahead and figure out what this is. What is 0.1 over 0.2? Well, that's 0.5, right? So there is a 50% chance that they ordered fries given that they ordered a Frosty, right? So the probability of their intersection, so like you can focus in here. I regret my colors so much. I want to know what's the probability they got fries given that they got a Frosty. So out of all of these people that got a Frosty, right, out of those 20% that got a Frosty, these people also got French fries, right? So it's 0.1 out of 0.2. So 50% of them, half of them, there's a 50% chance that they also got fries. Are ordering a Frosty and ordering fries independent? Does one impact the other? Is the probability of A times the probability of B, is that equal to their intersection? Right? It's a good way to figure it out. Does one occurring impact the other? So the probability of A, we know, is 0.2 times 0.8. Is that the same thing as their intersection? Right? So 0.2 times 0.8, I get 0.16. So are they independent? No, they're not independent. And that will be something that we can talk about more in different ways that we can figure out independence in our next lesson. Okay? Of course. Of course. Let's see if I got them all right. Right? Is the probability of ordering fries the same as the answer to D? No, right? Is another way to think about it. Probability of ordering fries is 0.7.1, right? That's 0.8. Right? You have, without even talking about the Frosty, there's going to be a larger probability of people that order fries. But once you narrow in that focus, it changes, which means that they are dependent on one another. Okay? So thinking about Venn diagrams, just a fun way to end it, right? Car, box. It's a Venn diagram, right? Boxcar. Your frequency of correct use. You probably don't use Facebook, so this probably isn't funny. We should probably say something different. I don't know what you guys use. TikTok. Instagram, maybe? Maybe that's still, maybe? Okay, so that's where I'm going to leave you guys. And we, as I said, like there's another probability lesson, and the next day, the next time, we will get a little bit more into some of these probabilities that are like what is independence and what happens when probabilities depend on one another. So we will be looking at that together next. So see you all soon.